Yeah, so dear students, welcome to yet another online tutorial on principles of communication system. So we were discussing about noise in FM, FM demodulation. Right. So this was the, and if you remember, this was the system noisy model. Right. So we have considered S of t our FM signal, then W of t is wide Gaussian noise. It was passed through a band pass filter, and then we like clipped off the amplitude fluctuations. Why this limiter was required? So when we are adding noise, what will happen is normally this S of t has a constant envelope, but when this noise is getting added, there will be fluctuations in envelope, but we are not interested in that. So what this limiter does is it will clip off the x of t. So here it is x of t, x of t almost near to zero, so that we are discarding the envelope. We are interested only in actually what zero crossing. So after the limiter, the wave will be somewhat like a square wave, not exactly square wave, with of course different duty cycle, right? So then what we tried is we tried to find out what does this theta t, right? So this theta t, this is what theta t we found in last class, right? So this theta t is being given to a discriminator, and we have seen a discriminator in turn has a slope circuit or a differentiator and an envelope detector. So this from here onwards we have to see, right? But before that, we'll just have a quick recap. This phi of t, right? So I believe you have the notes with you, right? So in that, phi of t is nothing but what the phase of our s of t, right? So we have represented s of t as AC cos 2 pi fct plus 2 pi kf integral 0 to t m of tau d tau, right? So this 2 pi kf, right? So this entire thing is actually what phi of t, right? So if we are representing s of t as a phasor, so how to represent it as a phasor? AC angle phi of t. So this phi of t is angle of this s of t. So that is what is this phi of t, right? Then what we did is we had this noise we represented it as actually what r of t cos 2 pi fct plus psi of t, right? If you remember, we have represented noise as r of t cos 2 pi fct plus psi of t. This is equivalent to what its phasor form r of t angle psi of t, right? This is equivalent to r of t angle psi of t. So this r of t is nothing but what the magnitude of noise phasor. R of t is nothing but magnitude of noise phasor. We have seen that is equal to square root of in phase component square plus quadrature component square, right? AC is carrier amplitude, carrier magnitude, and then psi of t is actually what the uh, phase of the noise phasor, and phi of t again this phi of t. So we found this is our theta of t. I'm not discussing again how we got the theta of t, right? So we have used a phasor approach, right, and representing it as a phasor, and after actually what applying some set of simplifications or assumptions, we came to this result theta of t. So now this theta of t is what is given to this discriminator, right? So the discriminator output, if it is v of t, that v of t will be, you can see we have discussed in last class itself, right? That will be 1 by 2 pi d by dt of theta of t, right? Its output will be 1 by 2 pi d by dt of theta of t, right? So we have discussed about discriminator even while we were discussing about actually what FM demodulation, right? At that time, I told discriminator is actually what similar to, or slope circuit is similar to a differentiator. So there is a reason why I told that, right? So you can explain that with the help of a property of Fourier transform. So anyhow, while discussing about noise, power, spectral density, I'll be doing that. So now, right, please keep in mind. So if you give theta of t is actually what phase of the input, whatever signal is given, right? So it's r angle theta of t to the discriminator, right? So the discriminator output will be equal to what 1 by 2 pi d by dt of theta of t. So here, please remember, we are not bothered about this amplitude variation part, right, before this discriminator, because it doesn't carry any information, right, as such, and we are using a limiter which will clip it off, right. So now this is what we have to find out, this v of t, right. So this v of t, after we pass this v of t through a low pass filter, right, we will get our output. Then we can um, find what is the output SNR and figure of merit. So before that, can anyone tell me, like, we need, what was the channel SNR we found and kept already, right? Channel SNR, it was equal to, can anyone tell me? You can type it in chat window. Those who have taken down notes, you can type it in chat window, right? What was the channel SNR for this particular case? The carrier power, or the S of t, the average power in S of t was AC square by 2. So it was AC square by 2, and the noise power within message bandwidth, it was N naught W. Noise power within bandwidth, it was actually what? N naught W. So this was SNRC. Can anyone cross verify it whether it is correct? Channel SNR, channel SNR. It's correct,
Yes,
right?
sir.
So
Correct.
it's right. AC square by 2 is the S of t's power, and N naught W is the noise power within a bandwidth of actually what, bandwidth of the message, right. So this we already have, right, these results we already have, right. Now we need to find what is 1 by 2 pi d by dt of theta of t, right. So here I'm going to make one more assumption. So we have this r of t and angle psi of t, right. So this is a noise process, right. This is a noise process. So you should remember this magnitude or envelope of this noise, it follows actually Rayleigh's distribution, right. So this r of t, it is Rayleigh's distribution. So we have studied different types of actually what distribution: uniform distribution, Gaussian distribution, Rayleigh's distribution, right, chi-square distribution, right. All those distributions you have learned, but right. So this what envelope of a narrowband noise process, it's actually what Rayleigh's distributed, and the phase will be uniform distributed over 0 to 2 pi, right. You just have to remember this, you don't have to what break your head, right. So just keep this in mind. It's r of t, the envelope is Rayleigh's distributed, and psi of t is uniform distributed. What do you mean by psi of t is uniform distributed? Which means the phase of this, right. So say p of psi of t, if I write probability, right, of psi of t, probability density function of psi of t, it will be something like this. It will be distributed from 0 to 2 pi, and the probability will be, right, 1 by 2 pi. It can take any value from 0 to 2 pi, right. It can take any value from 0 to 2 pi. So that is uniformly, and the phase being any given value between this is actually what equiprobable. It can be any value between 0 and 2 pi. So psi of t. So this psi, compared to this psi of t, this phi of t will be very small, right? So please keep in mind this phi of t. If you remember, it is actually what 2 pi kf into 0 to t m of tau of d2. This is nothing but what the deviation in phase of a modulated signal, right? So compared to the psi of t, phase of noise, phi of t will be very small, right. Pi of t will be very small. So what we can do is I can approximate this, right. Further I can, right, simplify this theta of t, right. So I'll write it here, right, as phi of t is much smaller compared to psi of t. We can further approximate, say, theta of t to be equal to, it was phi of t plus r of t by AC times sine of psi of t. That phi of t term we neglected compared to psi of t. Phi of t, as it is very small, so we have right neglected it. So this is our new. This is a final theta of t. Right. So now from this we'll find what is v of t. V of t is nothing but what the discriminator output. Right. So v of t we can write now. V of t, it is equal to 1 by 2 pi d by dt of theta of t. Right. V of t is equal to 1 by 2 pi d by dt of theta of t. Right. So how a slope circuit and an envelope detector can bring in the effect of what differentiation in time domain? That is a question. Right. So if you remember, I'll just give you a quick hint, and later on I'll explain it further. Right. So if you remember the slope circuit, can anyone tell me what was the transfer function of slope circuit? We have studied slope circuit. It is supposed to actually what give amplitude corresponding to what instantaneous frequency, amplitude variation corresponding to instantaneous frequency, or output amplitude should be proportional to input frequency, and it's a purely imaginary function. So it was j 2 pi, say f or something like this. So j 2 pi f, right? This was the transfer function. This was the transfer function. So we are giving, say, theta of t here. Theta of t is passed through, say, this j 2 pi f, and we are getting something here. So that is v of t, right? Or a j 2 pi f by, or jf or whatever, right? So this transfer function j 2 pi f. So it's actually what, when I say transfer function is j 2 pi f, it is equivalent to what, multiplying the theta of f, that is Fourier transform of theta of t with j 2 pi f, right? J 2 pi f. It is equivalent to what, multiplying Fourier transform with the transfer function. So this by a property, differentiation property of Fourier transform, right? We can justify. So just those who got it, it's fine. Otherwise, later on I'll explain it, right? So please keep this in mind now. So v of t is 1 by 2 pi d by dt of theta of t. This is equal to 1 by 2 pi d by dt of phi of t was actually what, 2 pi kf into integral 0 to t m of tau d tau, right? So plus 1 by 2 pi, 1 by 2 pi, this part is actually what, 1 by 2 pi d by dt of r of t by ac sine psi of t. So if you see, this theta t has two parts. One is actually what, one which has actually what, message, right? One which has, so maybe you can call it actually what, message part, and this is actually what, noise part, right? So you can see there is AC, carrier amplitude, is present in actually what, denominator of the noise part. So which means if you increase the carrier amplitude, right, the noise term will be further smaller, right? So this is what we have now, v of t. So can anyone tell me what is the resultant? So it is 1 by 2 pi, 1 by 2 pi as such, and there is actually what, 2 pi kf is a constant. This 2 pi and 2 pi will get cancelled, so kf only will be here. So it will be kf times d by, what is d by dt of in derivative of integral? So it becomes actually what, only the whatever is inside the integral, right? So it is m of t, right? Kf into m of t. So d by dt of integral 0 to m of dt, that is actually equal to actually what, m of t, plus this 1 by 2 pi, and AC it's a constant, so we can take it out. So 1 by 2 pi AC, this is d by dt of r of t sine psi of t. But what actually is this r of t sine psi of t, right? If you remember, right, if you remember, I'll draw the phasor, right? So this is phase equal to 0. This r of t, the phasor r of t was like this, and it made an angle psi of t with our reference, right? So this is actually what, If this is r of t, this is r of t, right? It made an angle psi of t with its reference. So if you see the projection onto the real axis, that will be what? N I of t, in phase component, right? The projection of r of t onto the real axis, that is in phase component, and projection of r of t onto the imaginary axis, right? So that will be quadrature component, right? So what will be this Ni of t? So r of t, Ni of t will be nothing but what? R of t cos psi t, right? And Nq of t will be what? R of t sine psi of t, right? So here we have actually what? R of t sine psi of t. This is nothing but what? Quadrature component of noise, right? This is nothing but what? Quadrature component of narrowband noise. So we have seen initially itself narrowband noise. We could represent it as in phase component times cos 2 pi fct, in phase component times to cos 2 pi fct minus quadrature phase component times sine 2 pi fct, right? So this is nothing but what? Nq of t. So I'll rewrite it like this. It is kf into m of t plus 1 by 2 pi ac times d by dt of nq of t, right? So this is our v of t. This is our v of t. This v of t, if we pass through a low pass filter, right? This v of t, if we pass through a low pass filter, right, which will allow the only up to the maximum frequency content of m of t. If you remember this m of t, it has a spectrum like this, right? This m of t has a spectrum like this. It will allow from 0 to w. So we will pass this entire thing, this v of t, through uh, a low pass filter. That's what the system model says, right? So once we get the, I'll just once again show you the system model, right? The system model says this v of t is passed through a low pass filter, right? This low pass filter will be an ideal low pass filter which will allow only up to the maximum frequency content present in our m of t, right? So this is what we have to do. So now we have this v of t, this v of t. If we pass this through a low pass filter, what will happen is this kf into m of t will be available as such, but we have this. So this is actually what message term. You can write it as actually what md of t, right? The output of low pass filter, right? When if v of t is passed through a low pass filter, the output what we'll get is the message part we can represent it as md of t, and this we can represent it as noise, demodulated noise, nd of t, right? That is v of t, right? So what happens is this noise, it may have say um, power lying outside the message bandwidth, but if you pass it through a low pass filter, what will happen? The out of the band noise component will be what? Suppressed, right? That's what will happen. Now what we need is we need to find snr at output, right? We need to find snr at output. For that we need to find actually what? Power in md of t divided by power in actually what? lpf of nd of t. This nd of t is low pass filtered, right? Then it's power. That is what we have to find. So are you clear till here, right? Till here, is it okay what we have done, right? Yeah. At least so we have noise message part, right? We have message part and noise part. So what will be power of message, right? What will be power in this? Average power within this kf into m of t, right? So maybe I'll write it below. Okay. And average power of this kf into m of t, this will be equal to kf square. We have a constant. If there is a constant, take square of it. Then we know power in m of t is equal to what? P, right? So average power in kf into m of t. This is actually what message power at the output, right? Message power at the output is kf square into p. But now we need to find what is the noise power at the output, right? We need to see what is the noise power at the output, right? So if it was ni of t or nq of t, right? If it was ni of t or nq of t, we know what is the spectral density of this. So maybe for those who don't remember what were these ni of t and nq of t, right? So initially, once again, I'll draw the system model, right? So this w of t is getting added to this is x of t is there. Then we are passing it through a band pass filter, and then we are passing it through a band pass filter, right? So here we are getting x of t, right? X of t is nothing but what? S of t plus n of t, right? This n of t, it is a narrow band pass noise, right? Narrow band noise, right? Narrow band pass noise, which means this w of t had a spectrum like this. It was n naught by 2 everywhere. This w of t had a power spectral density which is equal to n naught by 2 on both sides. But when you pass it through a band pass filter, what you'll get? So you'll get something like this, right? The output spectrum, right? Sn of f, right? Sn of f will be, right, it is minus fc and plus fc, and say this will be fc plus bt by 2, right? Fc plus bt by 2, and this will be fc minus bt by 2, right? And on both sides. So, and this will be n naught by 2. So this is actually what a narrow band noise. Why? Because it's not a white noise anymore. Why? Because white noise, when it is filtered by an ideal band pass filter, it will allow only these frequency contents. So this is a narrow band noise. So this is again a band pass signal, right? A band, which means which it is centered at fc, and it allows from fc minus bt by 2 to fc plus bt by 2. This is a band pass signal, right? So this band pass signal, normally for ease of analysis, we will represent it as actually what? Equivalent low pass signal, right? Equivalent low pass signal. So that will be n tilde of t, right? N tilde of t will be complex low pass equivalent of this n of t, right? Complex low pass equivalent of n of t. This ni of t and nq of t are nothing but what? Real part plus real part and imaginary part of complex low pass equivalent, right? This ni of t, in phase and quadrature phase component of, when I say in phase and quadrature phase component of noise, right? So those will be this n tilde of t, it will be a low pass, complex low pass. It will actually what will allow from bt by 2 to minus bt by 2, right? It will be a uh, n tilde of t will be complex low pass. So this, because of this, this ni of t and nq of t also will be low pass. So I assume you know what is the difference between band pass and low pass or base band, right? So we have this ni of t. This ni of t and nq of t has a power spectral density which will be like this, right? Ni of t and nq of t will have power spectral density. It's actually what? Bt by 2 to say bt by 2 to minus bt by 2, right? And it's right, this will be equal to say n naught, right? So this should be the power spectral density of our in phase and quadrature phase component. This is how the power spectral density of in phase and quadrature phase component will look like. So please remember, whereas the power spectral density of W of t was n naught by 2. So please do remember this. So this will be the PSD of Ni of t or Nq of t. It will be like this. Its value will be n naught, right? So why, if you ask me why, so the answer lies in the complex equivalent representation. So we have done a detailed video on that, right? How complex low pass equivalent of a band pass signal can be obtained along with the Hilbert transform, its properties and all. Right, right. If you want to know more about that, you can watch that video, right? Or else it's not exactly required for our discussion, right? So what you need to appreciate is the power spectral density of NQ of T is like this, right? So say S NQ of T will be like this. So it has frequency content from minus Vt by 2 to plus Vt by 2, and the spectral density right over this range is N naught. That is what you have to keep in mind, right? Now, what we have is the noise part. The noise part is 1 by 2 pi AC d by dt of NQ of T, right? So the noise part is it is 1 by 2 pi AC, then d by dt of NQ of T, right? So we need to find power of this or power spectral density of this, right? So why we are interested in power spectral density? Total power will be actually what? Power or area under the power spectral density, right? Total power within a given bandwidth will be area under the power spectral density, right? So this is our noise part. We don't know what is the power spectral density of this, but we have actually what this NQ of T here. We know what is the power spectral density of NQ of T. Power spectral density of NQ of T is this, right? It is like this, SNQ of T. But from this, can we find out what is the power spectral density of this ND of T, demodulated noise output? Can we find? That is the question, right? So, can anybody help me out? Is there any way which we can find out the power spectral density of uh, this ND of T? So before that, I'll just right. Uh, we'll just recollect one very important like result which we have like studied relate when we studied about actually what power spectral density, right? If we have an LTI system, right? If you have an LTI system with transfer function or frequency response h of f, and we are giving a signal with power spectral density Sn of f at the input, and if Sn O of f is actually the power spectral density at the output, we have studied this Sn O of f. Can anyone tell me what will be this? Those who tell this, right, will get um, one additional mark in second internal, one extra mark. Whoever is giving me the answer first, either after unmuting or typing it in here. So I'm telling we are
Multiply the input and the function.
multiply the input and functions. You mean to say this is h of f into Sn of f. This is
Yes.
not actually what Fourier transform. It is power spectral density. So maybe I think yeah. Are you clear about the difference between Fourier transform and power spectral density? Shavin, your answer is not correct. If it was Fourier transform, right, the answer would have been correct. But it's this Sn of f is not the Fourier transform. It's the power spectral density, right? So maybe I'll just you might have studied this, right? Maybe in DSP or in signals and system, right? So we'll just define, right? If x of t, say it's a random signal whose Fourier transform is x of f, right? X of t, its Fourier transform is x of f. It's not a periodic signal. It's a completely aperiodic signal. Let us assume, right? Then power spectral density, this PSD, it is defined as limit t tends to what in say infinite. One second. T tends to infinity mod of x of f square divided by t, right? This is how power spectral density is defined. Sorry, controls. Yeah. So this mode of x of f square, it will be actually what proportional to its energy, right? And t, say if if it is an aperiodic signal, right, we can assume the period is equal to infinity, right? We can assume the period to be equal to infinity, right? So then this energy per unit time, it's actually what it will be, a power, right? So power spectral density is defined like this. It's not, if it was x of f, if I'm giving x of f here, right, and the output would have been x of f into h of f, but it's not x of f. What I'm giving here is limit t tends to infinity, right, mode of x of f square divided by t, right? So then you can't write like, then what will be output is, we have discussed it already, it is mode of h of f square times Sn of f, right? This is mode of h of f square times Sn of f. You might have studied this in, you have studied random process, right?
Yes, sir.
In, which subject you have studied random process?
Elsa.
Yeah, Elsa. What is that?
Engineering, statistic, and probability. Something, something.
Yeah, yeah. Okay, okay. In that, yeah, okay, okay, fine. So in that, did you study about autocorrelation, power spectral density, all those
Yes, sir.
aspects? Right. So okay, there, like in properties of actually what power spectral density, right? You might have studied this. You might have forgotten, right? If you give, right, a signal, a random signal having power spectral density Sn of f at the input of an LTI system having transfer function h of f, right? The output will be equal to what? Mode of h of f square times Sn of f, right? So that's it. So that's the result. We don't have to dig deeper into it. So this result we have, right? This result we have. So with this result, right, can we find out what is the noise power in ND of t? Can we find out? So why? Because why I asked is actually, if this NQ of t, we know the spectral density of NQ of t. So it is SNQ of t. We already know that it is like this, right? So with that knowledge, can we find the power spectral density of ND of t? Can we find, right? So we can find, right? So there is a property. Maybe we'll just revisit one, a property, very basic property of Fourier transform, right? That is derivative property. Can anyone tell me what is this property? Derivative property of Fourier transform, right? So this property says if x of t, its Fourier transform is x of f, then Fourier transform of d by dt of x of t will be j 2 pi f times x of f, right? So d by dt of x of t, its Fourier transform will be j 2 pi f times x of f, right? Do you remember this? Right, at least you remember there is a differentiation property for Fourier transform. Yes, okay, yeah. So this is what is differentiation property. So when I say it as a property, right, it's actually what it means. If x of t, its Fourier transform is x of f, d by dt of x of t, its Fourier transform is j 2 pi f into x of f. What is the meaning of putting this double-sided arrow? Which means if I take Fourier transform, I'll get x of f. If I take inverse Fourier transform of x of f, I'll get back x of t. Right, that is the meaning. Wherever I am putting this double-sided arrow, right, it means it's a reversible operation, right? So this can be, right. I can write it, right. Can I write it like this, right? So if I have, say, if I'm giving x of t here, right, and I am passing it through an LTI system having impulse response j 2 pi f, right, I'm getting something. So what will be this something? Right. So you can x of t, its Fourier transform is capital X of f, and this is an LTI system, right? This is an LTI system. So the output will be X of f into H of f. That will be nothing but what, J 2 pi f into X of f. Are you clear with this idea? Right. So again, if you have confusion, what is transfer function? So h of t is impulse response. If you take Fourier transform of that, you will get actually what, h of f. We can call it transfer function. So you can either actually what, take consider transfer function as Laplace transform of actually what, impulse response, or Fourier transform of impulse response. Depends upon, right? Depends on the case, right? So it's, this is h of f. So x of t. Now I'm telling, if I pass x of t through an LTI system which has an impulse frequency response equal to j 2 pi f, the output will be x of f into j 2 pi f, right? So see this, right? So it's equivalent to what? It's equivalent to this x of f into j 2 pi f. It is equivalent to what? Differentiation in time domain. So it is equivalent to what? X of t, right? Passing through a differentiator, right? Differentiator, I'm getting d by dt of x of t. This is why I told, right? So this slope circuit, right? Slope circuit should have purely imaginary transfer function. Its transfer function should be a linear function of frequency, which means in effect actually what we are implementing, a differentiator in actually what, frequency domain. It will become actually what, a LTI system with transfer function j 2 pi f. Are you clear with this? At least some of you, if you got this idea, I would be happy. What we have discussed now. Why? Because this topic, when you read the textbook, it's actually what, it will be full of confusion, right? It will be full of confusion for you people, right? So how from one step to the other step. That's why I thought maybe we'll spend some time on this, right? Other topics which are easy, right, or which are straightforward, which doesn't have any like twists, right? You can learn it on your own. So now, so this idea we have. So d by dt in time domain is actually what, j 2 pi f in frequency domain. So again, we'll come back to our nd of t. This nd of t, it is equal to what was this nd of t? It is 1 by 2 pi ac times d by dt of nq of t, right? It is 1 by 2 pi ac times d by dt of nq of t. So I can represent, right, if I can imagine I am giving, right, this nq of t as input to some system, and it gives me nd of t as output, right? I'm giving nq of t as input to an LTI system, and it gives me nd of t, right? So what it should do is, it should be actually what, it should perform the h of t should be, right, 1 by 2 pi ac d by dt, right? What it should perform is, it should perform 1 by 2 pi ac d by dt. So this 1 by 2 pi ac, you can see it as a gain or attenuation or anything, right? This d by dt, right? So this it's a constant, right? It's a constant, right? So that it's like in frequency domain also, that will become a constant. But this d by dt becomes actually what, multiplication with j 2 pi f. So if I take frequency, if I convert this into frequency domain, it becomes actually what, this 1 by 2 pi ac will give you 1 by ac as such, but this d by dt becomes actually what, j 2 pi f. This d by dt becomes j 2 pi f. So if you give nq of t to some system which has a transfer function like this, you will get nd of t, right? You give nq of t to some system which has a transfer function like this, will give you nd of t, right? So now what is this transfer function? So we can simplify it further. This 2 pi and 2 pi will get cancelled, right? So what we have is jf by ac, right? So this NQ of t, oh sorry, given to a transfer system having transfer function JF by AC, right? NQ of t given to a system having transfer function JF by AC will give you ND of t, right? So now we know what is the spectral density of NQ of t, that is SN Q of t. We know what is the spectral density of NQ of t, that is SN Q of t. That is nothing but what? It is from minus Bt by 2 to plus Bt by 2 N naught, right? It is minus Bt by 2 to plus Bt by 2 N naught. So what will be the spectral density of this SND ND of F? Yeah, please tell me. So this is our H of F. H of F here is JF by AC. So mode of H of F, this H of F is actually what? Purely imaginary. Mode of H of F will be F by AC. Now I have told this much. Now please tell me what will be SND of F, right? What will be SND of F? So the last question I asked, right? No one gave correct answer, so no one will be getting 1 mark for your second internal, right? So this question, what will be SND of F? So you should use the idea, right? Yeah. Anyone is giving me answer?
F square by AC square into the input part.
So who's talking? Who's that?
Sounds.
F square by AC square times. Who was that? I just I couldn't.
7, sir. 7.
7. Okay, okay, yeah. 7. For this, did I tell I'll give 1 mark for second internal?
No, sir. No need, sir.
Simply right. Right. Thank you for not putting me in trouble. Right. And thank you so much for giving answer. That is the correct answer. What you have given is the correct answer. Right. So it will be SND of F will be mode of H of F square times SNQ of F. So that will be mode of H of F square will be F square by AC square, and this will be equal to N naught, right? This is N naught, and it is defined only when actually what? Mode F is less than Bt by 2, right? What is the meaning when I say mode F is less than Bt by 2? Which means F is between minus Bt by 2 and plus Bt by 2, right? So this is how it is defined. So we can write it here, right? We can write it here. This SND of F, right? SND of F, it is equal to, right? F square by AC, right? Then N naught, and it is between minus Bt by 2 less than or equal to F less than or equal to plus Bt by 2, right? Minus Bt by 2 less than or equal to F less than or equal to plus Bt by 2, right? So how to plot this now? How to plot this? So we can plot this easily. So this is our SN Q of F. This is our SN Q of F. So SN D of F also will be defined between plus minus Bt by 2 and plus Bt by 2. But when F is equal to 0, that will be equal to 0. Then it is actually what? Proportional to square, right? So it will be something like this. Right, proportional to square of F, right? So this will be S N D of F. This will be S N D of F. This is 0, and this is plus Bt by 2 and minus Bt by 2. So those who have confusion how whether this curve will be like this only, like it's a parabola, right? It's a parabola, F square, right? X square. Quadratic means it will be a parabola, right? And right, so if you want to try, you can try it out in GeoGebra, right? Whether or in MATLAB you can try whether you are getting this. Just F square and not by, so it should be AC square, right? It should be AC square, right? So this is the noise spectral density, right? Noise spectral density. So now what is the power? Noise power will be what? Area under this, right? Noise power will be area under this, but that's not it, right? What we are doing is, again, right, instead of going up, once again I'll draw the system model so that you'll be thorough with that, right? some W of t, right? This is S of t, right? So then we have band pass filter, right? Then we have a limiter, right? Then after limiter, what is the next block? We have discriminator, right? Then after discriminator, we have low pass filter, right? So this is about actually what discriminator output. SND, it's actually what discriminator output, right? So if V of t, right? So now when you pass this through a band pass filter having, right, which will allow from minus W to plus W, right? If you pass this through this signal, if you pass through a band pass filter, which will allow only from minus W to plus W, what will happen? It will be the band which is beyond W and minus W will be removed, right? So only this much will be there. This BT, if you remember, it is the bandwidth of our S of t, that is our FM modulated signal. So normally this FM modulated signal bandwidth will be much greater compared to what W, or W is nothing but what the maximum frequency content in message, right? If you remember by Carson's formula, right? What was Carson's formula? It gave us actually what approximate bandwidth BT. It was approximately equal to 2 delta F plus 2 FM, right? BT, it was approximately equal to 2 delta F plus 2 W or 2 FM, right? So this BT will be more compared to what W. So when you pass it through a low pass filter, the spectral density becomes actually what? It will be limited to minus W and plus W, right? So so we found the spectral density of noise part in V of t, right? But when we pass it through a low pass filter, it will be limited to minus W to W. So that's why I'm going to write. So here noise spectral density is S and D of F, right? And here noise spectral density will be S and O of F. I'll write S and O of F as it is actually a demodulated output, right? So S and O of F will be S and O of F. It will be equal to again F square by AC square times N naught. Here it's between actually what minus W to W, right? Minus W less than or equal to F less than or equal to plus W. So this is our output noise power. So whereas if this KF, we have a KF into M of t term also here, that KF into M of t term will be available as such at the output. Why? Because this M of t has frequencies from minus W to plus W, right? So that will be allowed by this LPF, right? So the output message power, right? Output message power will be KF square times P itself, right? So output message power will be KF square times P itself, but right, the output noise power will be decided by this power spectral density. So this is SN0 of F, right? So maybe I can plot this from this is minus W, this is plus W, this is 0, this is SNO of F. This is actually what PSD of noise at demodulator output, right? So now what will be noise power at output? Output noise power will be actually what area under this. Output noise power will be area under this, that is integral minus W to W F square by AC square N naught DF. So what is this? Right, this AC is actually what, so we can AC and N naught are constants, we can take them out. So it is N naught by AC square integral F square DF is actually what? F cube by 3, right? F cube by 3, and we have to apply the limit minus W to W. So this is equal to what? N naught divided by 3 AC square, right? So if you apply the limit, it will be actually what? If you apply plus W, it will be W cube minus of, what is minus W cube? It will be minus W cube only. So it will be minus of minus W cube. So this minus and minus will become plus, right? So this becomes N naught by 3 AC square. This W cube plus W cube is actually what? 2 W cube. So this is the output noise power, 2 N naught W cube by 3 AC square. Right. This is output noise power. So now what will be output SNR? Just see this, right? There is a term AC square in the denominator, which means if we can increase the noise power, right, it will what quieten the noise. If you can increase the carrier amplitude, if you increase carrier amplitude, it can quieten the noise at the output. So that's actually called noise. Sorry, what is the spelling of quietening? QUIE, right? Quietening effect. So please keep in mind. So what is the noise quietening effect? You can see the output noise power. It is proportional to, say, it is inversely proportional to AC square by 2, right? AC square by 2 is nothing but what? Carrier power, right? So inversely proportional to carrier power, right? Which means if you increase the carrier power, the noise power will be reduced, right? So that carrier power, so increasing the carrier power has a noise quietening effect. So that is actually that's called actually what? Noise quietening effect. So I just mentioned that. Please do remember, please note down and remember that what is noise quietening effect, right? So now SNR at the output of FM, SNR at the output of FM is equal to, what will be that? It is message power. Message power was, if you remember, it was kf square times P divided by noise power is this. So 2 N naught W divided by 3. So the 3 AC square will come on numerator. So it will be, right, 3 kf square P AC square by 2 N naught W, right? 3 kf square.
So W cube, right?
So sorry, W cube was, yeah. So sorry, W cube, right? So 2 N naught W cube, yeah. So 3 AF AC square KF P 2 N naught W cube. This is actually what? Output SNR, right? This is output SNR. Now what was channel SNR? If you remember SNR, thank you for correcting me. I think it was Sherwin, right? Thank you. Right, SNR channel SNR was AC square by 2 was the S of t's power, then N naught W, right? So the figure of merit will be equal to, right, FOM is equal to SNR at the output divided by SNR channel, right? So that is equal to, what is that? It is 3 AC square kf square P divided by N naught W. So if we do that, so we'll get 3 kf square P, remaining everything will be cancelled out, right, by W square. So here one W is there, right, and W cube is there, so that it will become actually what? W square. AC square and AC square will get cancelled. 2 N naught and 2 N naught will get cancelled, right? And so this will be remaining. So this is the figure of merit of FM. 3 kf square P by W square. But if you remember this, what is this P? P is nothing but what? Message power, right? Message power. If our message is AM cos omega t, right, or AM cos 2 pi FCT, this power, average power, will be equal to AM square by 2. Average power will be equal to AM square by 2, right? So maybe we can write it as actually what? 3 If for a single tone modulation, we can write it as 3 kf square am square by 2, right? So just now I'm suppressing this am square by 2 divided by w square. What actually is this kf into am? So now again we'll revisit, right? This kf, if you remember, it was called frequency sensitivity, right? In fm, right? In fm, so singleton FM, I meant, right? This KF is frequency sensitivity. KF into AM, this as such is called actually what? Frequency deviation. KF into FM is called frequency deviation. Frequency deviation. And right, so you can see this is proportional to actually this KF into FM is actually what? Frequency deviation. And KF into AM by W or delta F by W or delta F by FM. This was actually equal to what? Beta or deviation ratio, right? Delta F by W was deviation ratio. So you can see this is proportional to what? Square of deviation ratio or square of D square, right? This figure of merit, right? Figure of merit. So how I justified that? This kf into p, right? Kf into p will be proportional to actually what? P will be proportional to am square, right? P will be proportional to am square or maximum magnitude of the message square, right? Maximum magnitude of the message square. So this kf into am will become delta f. Kf into am divided by w will become actually what? This frequency deviation ratio, right? This delta f by fm, right? Or it is delta f by w. We can call it actually what? Modulation index or frequency deviation ratio, right? Frequency deviation ratio. So this is proportional to d square. This is proportional to d square, or this is proportional to actually what? Delta f square. This is proportional to delta f square. What does that mean, right? What does that mean? So if you remember by Carson's rule, the bandwidth, right, it was approximately equal to 2 times delta f into 1 plus 1 by beta, right? So bandwidth is proportional to delta f. If delta f is more, bandwidth will be more. If bandwidth is more, noise performance is better, right? So I'll write here, right, as, so this fm has a very beautiful property, right? If bandwidth increases, what happens? Figure of merit increases, which means noise performance increases. That is what we have told initially itself while comparing AM and FM, right? We told, I'll take two, 3 more minutes, right? So we told AM, right, there is no point in increasing the bandwidth of AM. Why? Because it can't give any better noise performance, whereas FM has a wonderful capability of giving better noise performance at the expense of added bandwidth. Do you, anyone remember that? We made a statement there. Anybody remember that? FM, right, while mentioning the properties, right, of any angle modulation as such, right, any angle modulation or FM, right, it has a capability of giving better noise performance at the expense of additional bandwidth. So I'll just conclude. So what is the figure of merit? Right, figure of merit of FM is, figure of merit of FM, it is equal to 3 kf square p divided by w square, right? This is proportional to d square. This we just remember, right? This d is nothing but what? Frequency deviation ratio, right? And in the case of a single tone modulation, it becomes actually what? Modulation index for single tone modulation. So this is about noise performance of FM, right? This is about noise performance of FM, right? So please, right, have a, you just try to recollect what we have done so far, right? So basically you have to remember this block diagram, this model, right? System model, right? System model is S of t getting added with the additive white Gaussian noise passed through a band pass filter, then frequency limited, right? Then it is passed through a discriminator, then at the end LPF and output, right? So finding this theta of t and also finding actually what the power spectral density of noise at the output. Those are two tricky parts which require some, say, prerequisite knowledge. So we have discussed that, right? So once we know that, then remaining everything is as usual, right? So here, finding theta of t and this PhD. So I think you already have notes in that, right? These things will be there, but these some of the explanations which I gave may be missing in that, right? So you can make use of this video, right? So that's it about uh, frequency or error, modulation, error performance, right? So then now we have to study what is capture effect, threshold effects, right? And we should also study about FM threshold reduction, then pre-emphasis and de-emphasis. With that, we'll finish this particular module. Maybe if possible, I'll try to finish this within next class, right? So that's it for today's session. If you have any doubt, you may please ask. Anybody has any doubt, right? Did anyone understand this? Anyone, right? Please feel free, right? You don't have to what. So is it understandable? Let me ask that. It is understandable, right? Yeah. So if you, which part is a little bit confusing in this? Maybe it would have been easier for you people. I myself might have actually what brought in some complications and confusions, right? Okay, fine. So if you have any doubt, you can ask. Otherwise, you can leave, right? Thank you so much for joining. Right. So this week we'll have a quiz, right? So it will be an open book quiz, right, based on whatever you have written. So till that quiz, I won't be posting this videos. Like this videos, I won't post only after the quiz. Right, last video, and even before that, and this video. Those three videos I'll be posting only after the quiz. Right, it will be an open book quiz. You can use your notes. Right. So that's it. Thank you so much for joining. You can leave.